Welcome back. In the last lecture, we were discussing about cause-effect relationship. Today's discussion is a bit of extension of that particular lecture, where we will discuss about some important constitutive relationship. Again, it is not an exhaustive session. Here, we will introduce certain important relationship between stress and strain and which is relevant in geomechanics. So, cause effect relationship, it describes how stress and strain is related, and we have seen that the most important aspect is constitutive matrix. Now, depending upon what sort of model you adopt for modeling a given situation, the constitutive matrix keeps changing. So, we will see some of the important constitutive relationship in today's lecture. Again, we will stick to the very same issue, that is solution to geomechanical problems. It should satisfy stress equilibrium strain displacement relationship, which ensures compatibility, the cause effect relationship, which is assumed to be linear for elastic behavior, this one, and the step C involves the constitutive behavior. So, today's discussion on constitutive relationship will focus around this particular point, that is the constitutive behavior. And we will skip this. We have already discussed set of discussion why it is essential for one to understand the problems or the solutions in geomechanics involves these three steps, the first three steps essentially, and plus this. In some cases, you will see that maybe stress equilibrium is satisfied, but the others may not. There are several problems in geomechanics or maybe specific to soil mechanics as well, where we do not achieve the other two, but stress equilibrium is obtained. So, how a particular method got evolved, it depends on that. Now, constitutive relationship in geomechanics, it is a cause effect relationship. That is what we in the beginning I told is an extension of last lecture session. Is a relationship between stress and strain, or you can say it is a relationship between force acting on a material and the resulting displacement. The real stress strain relationship of soils or rocks, it may be complex in nature. In most of the time, we have seen, and everybody who is an engineer or a non-engineer, they will be able to understand this very fact that soil is pretty complex and very hard to understand, and whatever we say, still there will be some gap left in our understanding. There's so much of uncertainties are there associated with soil behavior. So, a real stress strain behavior is beyond question. What we can do is to understand or to develop models which are close to or which closely simulate the real soil behavior, and this is simplified. So, we understand the fact that it is complex. So, through some idealization, this particular relationship is simplified by idealization and are required for the development of mathematical models. So, first let us begin with a very simple model, which is linear elastic behavior. One may always tell why we should discuss linear elastic model at all in soil mechanics, because most of the cases we understand soil behaves non-linearly. But there are certain aspects, just because of its simplicity and simple mathematical formulations and minimal requirements, this model is very popular. So, linear elastic model, we always start with that, and there are very specific problems which consider it to be elastic in nature. Now, how far it is true, that is a question mark, but because of its simplicity and to the fact that the results are not really off, under certain circumstances we can even apply linear elastic model for simulating the behavior of soils, but not always. It is far from reality. As you can see, the y axis is the stress and the x axis is strain, and this is a simple linear elastic behavior where it is represented by a straight line, and we know that it is non-hysteretic, means it traces back the same path. So, linear elastic model, the load result in stresses which are well within the yield limit. Now, this is the point. Now, if the loading acting on the soil is fairly less as compared to its strength, we can still say that it is within the elastic limit, and this is the whole basis of working stress method and the logic of applying factor of safety. We apply a high factor of safety and ensure that the stresses which are acting on that particular body or soil is well within, or maybe it is at par or slightly below the elastic limit, or to be very specific in geomechanics, the yield limit. Now, yield limit is the point beyond which the plastic strain sets in or the plastic behavior starts happening. Let us say that we have marked up to here at up to this particular point. Now, if the same material is further loaded, it may exhibit a non-linear behavior. So, this point can be treated as yield limit. So, we will come to that a bit later. So, linear elastic consideration ensures, or we make a presumption that the stresses are well within the elastic limit or the yield limit. Yes, I have already told this, it is popular due to its simplicity and the requirement of less number of parameters. Obviously, this we have seen in the last lecture. We have seen that for linear elastic cause effect relationship, you need to know only two parameters, and what are they? Modulus of elasticity E and the Poisson's ratio mu. So, with this one can readily model the behavior of soils or maybe geomaterials. Now, there is an inherent assumption involved in most of these models, which is directions of principal incremental stress and incremental strain coincide, means the direction in which the incremental stress is, it is the same direction for the principal incremental strain. So, that is what it means, both coincides. Now, when it comes to plastic formulations, it may or may not coincide. So, there are various other models, but in linear elastic, for that matter, various other elastic models, you have this inherent assumption that the incremental stress and the incremental strain are in the same direction. Incremental, why incremental? We are talking about a very small increment of stresses, that we will come to know a bit later why incremental is important. And this model essentially corresponds to homogeneous isotropic low stress. That is what I mean. If we want to ensure that it is working stress, then it has to be under a low stress condition, and material parameters independent of stress level. Now, if you consider this particular plot, you can see that E, the value of E remains constant up to this particular limit, yield limit. Whatever be the strain level, we can say that these are different levels of stresses and these are various levels of strain. Now, whatever be the stress level and the strain level, if your body is considered to be linear elastic in nature, the parameters or the material parameters, which is E and mu, is considered to be constant, or rather it is constant, and it is independent of the stress level. Okay. So, linear elastic only this particular requirement is there, and it essentially confirms to low stress. So, if the material behavior is linear, then the modulus of elasticity and Poisson's ratio are constants, which I have already discussed. So, it does not simulate the important aspects of soil behavior. So, in the absence of other complex models, one can always use linear elastic model, but with a proper understanding that it is not going to simulate the real soil behavior. But it is not fully true, this statement. There are certain situations where soil exhibit some sort of elasticity, and one good example is an over consolidated state where the soil is fairly stiff, and when it is stiff it can exhibit elasticity. Again, that elasticity is also subject to certain conditions. Beyond certain point it again subject to yield. So, it is condition specific. It is not like other materials. For soils, what type of behavior it would exhibit, it is also condition specific. Under certain conditions it can exhibit elastic behavior. So, this model would be more relevant for structural elements like retaining walls, because retaining walls are very widely used and it is an important aspect of geotechnical engineering. So, for modeling those, linear elastic models may be important. Okay, so now we will go to some other extension of the linear elastic model. Now we will come to bilinear model. In fact, bilinear models are, or it represents non-linearity, but you are doing some sort of adjustment, or you are showing that non-linearity using two different lines. So, that is why it is called bilinear model. Material behaves linear elastic till it reaches yield stress. We will be discussing about yield stress in detail in module 4, but here we just need to understand it is the point beyond which the plastic behavior starts. So, material behaves linear elastic till it reaches yield stress and then remains constant with strain. So, what it means is that the stress strain behavior, it is of certain manner till it reaches yield limit or yield stress, and beyond which it remains constant. Now, this constant means depending upon the formulations there will be some sort of changes. As constant, we will come to that in the discussion. Material parameters remains constant till it reaches failure condition. So, here we will discuss two bilinear model. The first one is elastic, perfectly plastic. So, you can see here that we are not talking only about elasticity. It is a pure elastic model. It is elastic, perfectly plastic. It includes plasticity behavior as well. So, here it is not a pure elastic model, it is rather elastic and plastic response both are taken care. But since it is an approximation using linear lines, it has been discussed now. You can see that there are two well defined, 1 and 2 well defined behavior, one is in this manner, one is in this manner, there are two straight lines. So, that is why it is called bilinear model. And elastic, perfectly plastic, you can see that from this point to this point you can see it is a linear trend and the material constants E and mu remains constant. So, this part takes care of the elastic behavior. Now, after reaching the yield point, then nothing changes. It has gone to its plastic state, just directly from the elastic limit it goes to its plastic state or the failure state. So, here you can see that stress remains constant, whereas the strain increases to a large deformation, but at constant stress condition. So, here it remains constant, whereas immediately after the yield point it remains constant, the stress remains constant. So, one more requirement in this particular model is one should be knowing what is the yield point. So, apart from E and mu, one should be knowing what is the yield point. The Mohr Coulomb failure envelope using C and phi is a good example of this, okay, for setting the yield point. So, this we know that this is the point at which the soil will fail. So, it is assumed up to that particular point it behaves elastically. This is also far from reality. In real condition, soil is not going to reach to its plastic state just at its yield point or at its failure state at its yield point. There are certain other type of behavior as well in the real soil behavior. Now, we have discussed about elastic, perfectly plastic. A similar model or maybe a subset of this is rigid, perfectly plastic, where the material is considered to be having no deformation till it reaches the yield point. You can see here there is no elastic portion of the curve here. In the earlier case you have elastic portion, here there is no elastic portion. Directly it goes to its failure state at its yield point. So, in this case only one parameter need to be known, and that is the yield stress or the yield point or the failure state, whatever be, but the response both are same. So, here it jumps to its yield condition directly. Now, these are different models which are used. So, once it reaches failure, elastic parameters are set to a value close to 0. Now, I would be very cautious to use this term, it is close to 0, because you will see that in certain finite element modeling, if it is set equal to 0, then there will be a problem. So, it is given a very small value close to 0. So, that is why I have used this particular term, and we have written here not necessarily equal to 0, even though we know according to the model it is 0, but it is set close to 0. If the stress state is unloaded exactly at the yield point, it comes back to its pre-failure value, which means I am not telling any point here, I am telling at this particular point. If the unloading is done, then it gets back to its original. Oh, okay. So, that is the issue related with this particular model. Once at yield, it undergoes some sort of plastic deformation, but here even it has reached at its yield point, and if you unload, it is bound to come back to its pre-failure state. Elastic parameters defines the pre-failure behavior. So, pre-failure behavior is defined by elastic parameters. Further, it needs parameters to define the failure surface. That is what I told, you need to know the yield point as well. This behavior is elastic and perfectly plastic, and these are used in limit analysis problems that you use in soil mechanics, where in the case of limit analysis it also satisfies the stress strain relationship, but it needs to know what is the limit value according to certain theorem. So, we will not go into the details of limit analysis, but this becomes the foundation block for limit analysis used in geotechnical engineering. If the elastic deformation is negligible, then it is assumed to be rigid, perfectly plastic, only under the condition that we neglect the elastic deformation. It is so less that it is neglected and straight away it is going to its failure. So, limit analysis of slope stability is a classical example of this. Now, we will quickly discuss about certain other model which are in line with this bilinear modeling, which is linear, elastic, linear hardening. Now, I am introducing another term which is known as hardening. hardening behavior. It is a typical behavior exhibited by plastic response of a material after it reaches its yield limit, where the stress increases with strain, as you can see here. So, this particular point is the yield limit, where it shows the transition from elastic state to the plastic state. Obviously, the stiffness portion has reduced. Now, this portion is called the hardening state, and this is the linear elastic portion, but it also try to capture the linear hardening. So, this in fact it is not linear, but here it is approximated as linear hardening. Okay. So, this is linear elastic, linear hardening. Now, another aspect of it is linear elastic, non-linear hardening. Now, this particular portion is represented by non-linear behavior. So, both captures the hardening portion of the soil behavior, which means I will again add here hardening, it refers to a sort of volume change that is happening during shearing. It is a kind of response. In linear elastic or maybe other bilinear model that we discussed, this portion of volume change during shearing is not incorporated. So, beyond yield point there will be a volume change. Now, this volume change results in such behavior which is hardening, or another aspect is softening. So, we will discuss those in detail later, but here we just need to understand this particular model takes into account the hardening behavior by certain line, and in this case it is a non-linear behavior. We have discussed about linear elastic. Now, the next set, which is a bit of refinement over the linear elastic model, is non-linear elastic behavior, where the material response is considered to be non-linear but elastic in nature. How do you ensure this? This is a non-linear response, is a curve response, but if you unload at any point of time, this particular curve traces back. So, that is the one very simple definition of elastic behavior. It does not show hysteretic behavior. The manner in which you load it traces back. So, that is what is shown here. This is the loading and this is the unloading. So, non-linearity is in the curvature, it is there, but it exhibits the elastic behavior. It does not result in any sort of permanent deformation, and it traces back. This is more realistic than the linear elastic behavior for soils. Material parameters are dependent on stress and or strain level. Now, this we need to understand carefully, and that is why the incremental strain becomes important. Like at every point, if you consider along this curve and we draw a tangent at these points. For example, if I draw a tangent here, if I draw a tangent here, if I draw a tangent here, we can see that the stress by strain, or rather the elastic constant, that keeps changing at every point on the curve. So, that is why we call it as tangential increment. The increment is represented by tangent at a particular point on the curve, and that gives you what is the elastic constant or material parameters. So, that is what it is written here. So, material parameters are dependent on stress and or strain level. So, if you consider this is a particular stress level or this is a particular strain level, similarly you have this as the stress level and this as the strain level. So, at every stress strain level, the material constants or the material parameters keeps changing. So, isotropic assumption is valid to ensure that it has only two parameters. If it is anisotropic, then again the number of parameters keeps changing, because in different direction the parameters will be different. Any of the two material properties are chosen. Now, we know that this is an elastic analysis, and hence the very straightforward choice is E and mu. But we can also represent the model in terms of bulk modulus and shear modulus. Why specifically bulk modulus and shear modulus? Because one represents the volume change behavior and the other represents the shearing behavior, because it is associated with shear. In soil mechanics, K and G are preferred, as the soil behavior is represented in terms of mean stress and deviatoric stress. So, when it comes to model that uses invariance, it is found that mostly K and G are preferred. Why? Because the same reason what I just discussed, it represents the volume change aspect and the shearing aspect. We have seen in the earlier lectures that we have already told these are decoupled, which means to say we study from the given stress tensor, we decouple the mean stress and the deviatoric stress, and we study the volume change behavior keeping the shape constant, and we study the shearing behavior keeping the volume constant. So, these are taken one at a time. So, volume change and shearing in a decoupled manner, and this is purely from simplicity point of view. The actual soil behavior, it does not follow a decoupled behavior. So, that is all about nonlinear elastic behavior. Another refinement of this is nonlinear elastic, nonlinear hardening. So, this portion gets added up. Here it is not, it is up to yielding. So, beyond yielding, the hardening response is also treated as nonlinear. Another model is KG model, where K stands for bulk modulus and G stands for shear modulus. So, the tangential bulk modulus, that is incremental at a particular point, and shear modulus are defined in terms of stress invariance. How? It is defined in terms of P dash and J2. What is J2? J2 is the second invariant of deviatoric stress tensor. Now, probably you will understand why we have discussed these invariants before. So, it is just not discussed. Why? Because these invariants are very much used in geomechanics modeling, or to express certain models, these invariants are used. So, these invariants are very important. So, here in the KG model, both the bulk modulus and the shear modulus, they are expressed in terms of stress invariance, that is the mean stress P dash and root J2, where K naught, alpha K, G naught, alpha G and beta G, these are all parameters of the model. Okay. So, we need to determine these parameters in order to apply KG model. The stress strain curve for this model is given, that is P dash versus epsilon V, that is mean stress upon volumetric strain. It is always associated with volumetric strain, and the deviatoric stress, that is J2, root J2, is associated with deviatoric strain. So, ED here represents deviatoric strain. So, what is deviatoric strain? The expression is given here. Again, it depends upon the various definitions of deviatoric stress or deviatoric strain. There is no specific guideline as such. Different models assume different forms of deviatoric stress strain expression. For this, in this particular model, the deviatoric strain is given by 2 by root 6 epsilon 1 minus epsilon 2 square plus epsilon 2 minus epsilon 3 square plus epsilon 3 minus epsilon 1 square in root. So, stress strain curve, one important aspect which we need to note here is in P dash versus epsilon V, the slope keeps increasing in this direction, which means to say the bulk modulus keeps increasing, whereas in the case of J2, root J2 versus deviatoric strain, you can see that the bulk modulus keeps reducing as the soil gets more and more stressed or sheared. So, you can see that the shear modulus reduces, whereas the bulk modulus increases. So, this is a typical stress strain curve representation which we use in KG model. So, next is hyperbolic model. Hyperbolic model, it is a relationship between accumulated stress to accumulated strain. Now, till now we have been talking mostly about the incremental stress and incremental strain. Here it is the cumulative effect of stress and strain. It was originally used, hyperbolic model was developed to present undrained triaxial test based on two parameters in which Poisson's ratio is equal to 0.5. I think this point you remember in the previous lectures we have already discussed this particular point. Poisson's ratio is set to 0.5 for undrained condition. Why? The bulk modulus becomes infinity and then there is no volume change. So, original model is represented by this hyperbolic equation where sigma 1 minus sigma 3 is the deviatoric stress, epsilon divided by A plus B into epsilon, where epsilon is the strain. Sigma 1, sigma 3 major and minor principal stresses, epsilon is the axial strain and A, B are the material constants. So, it looks like this, and the initial tangent modulus is shown here EI and the asymptote is shown here sigma 1 minus sigma 3 F. Asymptote means the final value at which the failure happens is represented by this curve becomes asymptotic, and that particular value is shown by sigma 1 minus sigma 3 F, and the initial tangent modulus EI is shown here. Now, it is shown that the initial tangent modulus EI is equal to 1 by A, and the failure value, that is sigma 1 minus sigma 3 F, that is the asymptote value, is equal to 1 by B. So, both these material constants A and B has some meaning in the hyperbolic model, that is 1 by A is EI and 1 by B is sigma 1 minus sigma 3 F. So, based on our stress strain data, if we can determine A and B, then the constants EI and the final value is known. So, for that, if we rearrange the hyperbolic model in this particular form, that is epsilon divided by sigma 1 minus sigma 3, it is equal to A plus B into epsilon. Now, this is a linear response, A plus B into epsilon. So, plotting laboratory data to this rearranged form, A and B can be determined. How? If you plot epsilon by sigma 1 minus sigma 3, this portion as a function of epsilon, this, then we are likely to get a straight line and the intercept is A and the slope is B. So, once you get A and B, EI and sigma 1 minus sigma 3 at failure or the asymptotic value can be determined. So, another model is small strain stiffness model, which is based on the understanding. This is a relatively newer model as compared to the earlier discussed models which were very much there in the literature. Now, this particular model, small strain stiffness model, is based on the understanding that the soil undergoes significant changes in stiffness when initially subjected to a small changes in strain. That means, if it is subjected to for the first time or initially a small changes in strain, it can bring about a significant change in stiffness. Now, none of the above models what we have discussed can capture this particular behavior. So, this particular model has been developed. The existing models, they are not capable for capturing the stiffness change at small strain. So, small strain stiffness model, it was developed to simulate the soil behavior in small strain range, not applicable for large strain where failure occurs. So, frankly, we are not discussing about the failure in this model, we want to capture this small strain behavior. So, the variation of bulk and shear moduli are expressed as secant modulus. Now, what is secant modulus? It is expressed as G sec and K sec. So, what is the secant modulus. So, if this is sigma versus epsilon and it represents a nonlinear curve. So, this is the initial tangent modulus and this is tangent modulus. So, if I want to find out the modulus here, the secant modulus is this. So, this slope is the secant modulus. So, here the variation of bulk and shear moduli, they are expressed in terms of secant modulus, and the expression is given as g sec by p dash. Again it is in terms of invariance, a plus b cos alpha log 10 ed by root 3 c raised to gamma and k sec by p dash is equal to r plus s cos delta log 10 epsilon v by t raised to eta. So, there are lots of parameters along with this small strain stiffness model. So, practically it becomes difficult in certain cases where the number of parameters are too large. So, you need to determine all of those. So, that becomes sometimes a deterrent for choosing certain models, and why models like linear elastic models are so popular. So, all these are material constants, whatever has been discussed here, they are material constants, and hence those issues makes these model less popular, but for taking care of specific behavior one need to go for these models. So, where ED in this expression is deviatoric strain, we have already explained, epsilon V is the volumetric strain, and these are strain invariants. Before ending this lecture, we need to actually discuss what is the real behavior and how it can be captured for problems in geomechanics, and that is elastoplastic behavior, a more realistic model. A different version of elastoplastic behavior we have discussed in bilinear section, where we discussed about elastic perfectly plastic and rigid perfectly plastic. This is yet another and more refined and considerable improvement of those, where we discuss about the elastic. As you can see here, this is the elastic portion, here the yielding happens, the plastic behavior sets in. So, elastic, yielding and plastic. Now, if we try to unload it from this particular point, it is not going to trace back. Now, that is the difference between nonlinear elastic and elastoplastic behavior. In this case, it is not tracing back, rather it takes another route, and which is more or less parallel to this linear portion. So, it comes down, and if it is again loaded, it traces more or less the same parallel as that of elastic behavior. Why? Possibly it is because it has been loaded up to this. Now, whatever loading you are making here, it is always less than the load which it has been subjected to. So, that is why here this is the elastic response, this is the plastic response, here it is unloading and reloading, and then beyond a certain point again the plastic response sets in. So, here another important aspect to be looked at is this is the strain. Now, from here we have unloaded. So, whatever strain it has regained, that is elastic portion of the strain, and whatever it has undergone the permanent setting or permanent deformation, that portion is given by the plastic strain. So, the total strain in elastoplastic response is the summation of elastic strain and plastic strain. So, that is what is shown here. So, knowledge of stress strain behavior beyond yielding is important to understand failure. This we have already seen. Unless we know where it is going to fail, it is difficult. So, now here there is a sort of behavior which the soil exhibit beyond yielding. So, that is captured in elastoplastic models. Stress strain relationship, it is not unique beyond yielding, which means to say once it has yielded, then the stress strain response is not unique the way we have it for elastic response. And strain at a point not only depends on the stress level, but it also depends on the loading history, that is the point P. What it means to say is, let us say it has taken, this is the elastic portion, then there is plastic deformation that is happening. At this point it is unloaded. Now let us say that it reaches this particular point P. So we have reached this particular point P. So what it means, strain at a point, that is strain at point P, this one, it not only depends on the stress level. Now here at this particular point you can say that this is the stress level. Now from here it is loaded, it can take this particular route to P, or it can go, it can yield and it can come back here, and here there is a point P. Now the strain at a point, here it has crossed the strain and then it is unloaded. So strain at a point, it not only depends on the stress level but also the loading history at the point P. So it is not only the stress level, if I know a particular stress level, this is the strain. It is not like that. That strain would be a result of the stress history as well, or the loading history as well, and in soils this is extremely important. What is the loading history? And that is how the concept of normally consolidated and over consolidated or dense or loose state comes into picture. So what is the stress history or loading history also play a major role in defining what is the strain which the body has undergone. In this case it is purely elastic strain, whereas in this case it has undergone some plastic deformation and certain regaining has happened. So totally these are different path which it has followed. A realistic model for soil behavior where both elastic and plastic behavior is incorporated. The models can account for yielding, hardening and softening. We will come to hardening and softening later. So here it is yielding and it is hardening. Now this is a typical behavior of a ductile material where with stress the strain is increasing. So that is a typical behavior of hardening, and in the case of softening, after yielding the stress reduces with strain. Now why this behavior, we will see it later in the subsequent modules. So this is a typical behavior of brittle material. So yielding with hardening, yielding with softening. So these two aspects can be captured by different elastoplastic models. So some similarities between hardening and oedometer results. So if you replot the stress strain plot like this, so what I have changed, I have interchanged the x and y axis. Now the strain is on y axis and stress is on x axis. You can see the same plot as before. So A to B and then yielding, and then the plastic behavior happens. From here it is unloaded. So this is unloading reloading path CD, which is more or less parallel to AB. Now if you compare this with a given oedometer result, you can find that there is a sort of similarity. Here it is E versus log sigma V dash. This is a very popular representation of oedometer results, where you talk about the virgin consolidation line and swelling reloading line. You can see that this particular response of this is more or less similar to this behavior, this particular behavior, whereas swelling reloading line, it is more or less mimicking this particular behavior. So swelling reloading line is similar to the unload reload plot of this particular stress strain behavior CDC. So you can consider this as the yielding point, which is somewhat similar to here, or maybe similar to here. Swelling reloading line is similar to the unload reload plot, that is CDC of strain stress plot, because it is plotted on y axis. Here this particular line and this particular line, it closely resembles, and the way in which it responds is also similar. CDC exhibit elastic behavior, so does the swelling reloading line, and it has something to do with the stress history. Virgin consolidation line induces permanent plastic strain. So, beyond BC, so this is the yield point. So, beyond yield point it induces plastic deformation, and same is the case with the virgin consolidation line, where there is permanent setting which is happening, and this is similar to the yielded strain hardening behavior of BCE. So, this is yield point and this is the hardening behavior BCE. So, this and the virgin consolidation line behavior, these are same. So, to summarize today's lecture, the simplistic linear isotropic elastic models require only two material parameters, and that is why it is simple. In nonlinear elastic models, material parameters vary with stress strain level, whereas in linear elastic model it is constant. The nonlinear elastic models, it cannot capture the volume change behavior of soils during shearing. We are talking about the hardening and softening behavior. All the elastic models inherently assume the same direction of incremental stress and strain. Most of the linear elastic and nonlinear elastic models cannot capture the real soil behavior. We have already explained that. Elastoplastic models, they have been developed to capture the nonlinear stress strain behavior of soils fairly well. It can account for the strain hardening and strain softening response during shearing. And beyond yielding, the behavior of soil is not unique. But having said that, we also need to keep in mind that as we proceed from linear elastic to elastoplastic models, the complexity of mathematical solution also increases and the computational effort also increases. So, that we have to keep in mind. So, the various aspects related to anisotropy is not considered in this course. So, mostly we will confine all our discussion to isotropic soil behavior. So, that is all for this particular lecture. We have just discussed some important aspects of the cause effect relationship in terms of constitutive behavior or constitutive model behavior. So, we have discussed about different models which relates the stress and the strain, but let me again make a point here that this is not an exhaustive discussion. There are several aspects to what we have discussed till now. This is only for you to get oriented towards such constitutive behavior. So, with this we will end this particular lecture, and till now we have been focusing mostly on three-dimensional aspect. Now, for actual problem solving, we need to transform this 3D to 2D behavior for simplicity. So, for certain problems one can always idealize a given 3D problem to 2D. So, that will be seen in the next lecture.